Assalamualaikum and a very good day to the panel. I am Putri Izzah Zuhaira here as the department's representative. Thank you all for coming here today. Today's technical briefing focuses on the critical shift in orthopedic surgery. The move from permanent structural reinforcements to bioresorbable system. For decades, 316L stainless steel has been our primary agent for bone repair. However, these implants are too permanent. They remain in the physiological environment long after the bone has reached full union, leading to long-term complications. Today, we propose a new transition to magnesium, the metal engineered to perform and disappear. Let's look at the chemical specification. Magnesium, atomic number of 12, sits in group 2 of the periodic table. At the subatomic level, its 3s2 valence electrons makes it highly susceptible to oxidation. While this reaction is typically liable in traditional engineering, in a biomedical context, it is our greatest asset. Magnesium is an essential nutrient. Our bodies already store approximately 60% of our natural magnesium within the skeletal system. This makes it the most biocompatible structural metal available for high-load applications. You might ask why we should phase out of stainless steel and cobalt chrome. Well, the issue lies in the crystal lattice. These traditional metals possess a rigid face-centered cubic structure, resulting in a modulus of elasticity that is far higher than the human bone. This disparity causes stress shielding. The rigid implant absorbs the mechanical load, depriving the underlying bone the stress it needs to maintain density. The result, the bone becomes porous and weak. Furthermore, because these metals are chemically inert, they require a second high-cost surgical machine for extraction once healing is complete. The primary challenge with pure magnesium is its high chemical reactivity. Upon implantation, it undergoes an electrochemical corrosion reaction with tissue fluids, releasing magnesium ions, hydroxide ions, and hydrogen gas. To control this, we don't just use one alloy, we have an entire profile tailored for specific surgical missions. For example, JDBM, our balance alloy. It is used for larger structural supports like vascular stents because it maintains the mechanical integrity for up to 6 months in vivo. AZ31 and A221. Now these are early generation alloys use elements like aluminium and zinc. While high strength, they are often used in smaller temporary rolls due to their very sharp degradation profiles. By strategically selecting these elements, whether it's adding zinc-chromium for grain refinement or zinc for corrosion resistance, we can fine-tune the implant to match the exact healing timeline of the target tissue. The data confirms a decisive mechanical advantage. Unlike permanent stainless steel, which is far stiffer than human tissue, magnesium-based alloys, like as I mentioned before, offer a modulus of elasticity approximately 45 GPa and a density of 1.74. These specifications closely align with the natural human bone, effectively eliminating the stress shielding effect that causes bone resorption and secondary fracture in traditional implants. Traditional metallic implants often necessitate a secondary surgical removal, increasing physical trauma and placing massive financial burden on the healthcare system. By developing bioresorbable magnesium, we eliminate follow-up operations entirely. The implants perform its mission and then safely degrades and is absorbed by the body, leaving behind only healthy regenerated bone. Team, We are moving from clunky permanent hardware to smart kinetic chemistry. This concludes my report for the CHM 678 meeting. I am Putri Zazuhaira. Thank you for your time.